What I want to do in this video is to revisit an old concept that we learned in intro physics called work and build an intuition for it so that we can solve more complicated problems in the future. So we have work definition on the screen. We have W is equal to the force exerted on an object dotted with the object's displacement. Right? So the work done on an object over some displacement dr, delta r. So the first thing that I want to point out is that there is no arrow over the W, which means that it is a scalar quantity. Hello, different color please. Scalar. It is a scalar quantity, meaning that it has a magnitude, it has a strength, it has, you can put a number to it, but it does not have a direction. So perhaps a good example of an analogy is mass. So my mass is 86 kilograms, it's about 190 pounds, and that's just a property of me, right? I couldn't put a direction to it. I couldn't say that it's 86 kilograms downward. You know, I can eat more and then gain some mass, and I can maybe work out and perhaps I could lose some mass. But I wouldn't be losing that mass in the downward direction, and I wouldn't be gaining it in the upward direction. Yeah, it doesn't make any sense. So mass doesn't have a direction, and work doesn't have a direction either. So what I have here are two vectors, the vector for force and the vector for displacement. Right? And it's pretty easy to wrap your brain around the idea that force has a direction. We've been talking about force, and of course you addressed it in your intro physics too. A simple example is that the force of gravity on the surface of the Earth is pointed downwards towards the center of the Earth. Right, that makes some good sense. You can drop an object and prove that pretty easily. Let's build up, and maybe it's been a while since you've worked with vectors, so let's build up an idea of what I mean by a displacement, or how I define it. So I'm going to draw my axes here, and here we go. X, I'm my X, I'm my Y, and I'm my Z. All right? And I'm going to say that our object starts at this spot, some vector X, Y, Z, and it ends here. All right? So I'm going to draw an arrow representing the vector, and this is going to be my position vector R. I'm going to label that R1. Let's go with Ri, our initial. That has an arrow on top, it represents a vector. And then I'm going to draw another arrow going from the center, always from the origin to another place. So my position vector Rf. And what I'm going to do now is I'm going to connect them. I'm just going to draw a line, an arrow, going from my initial to my final position. And I'm going to call that delta R. Delta R. Okay, so I had some initial position Ri and some final position Rf, and the thing that connects the two is defined as delta R is equal to Rf minus Ri. Oops. I was trying to do that one in yellow. Select Rf minus Ri. Alright, and then keep in mind that this is a line. The vector is a line connecting these 2 points together. Okay, so the next thing that I want to talk about is this dot in the middle. There are two ways to multiply a vector with another vector. It's the dot product and the cross product. And one has to do with parallel components, and that is the dot product. The other one is perpendicular, or dealing with perpendicular components. That's the cross product. This is the dot product here. And it is defined as, let's do light blue. It is defined as A dot B is equal to the magnitude of A, so magnitude, no direction, times the magnitude of B times cosine of theta, where theta represents the angle between the two. So I guess I could draw them, but maybe I'll draw them for F and delta R. So say that I have this classic example of work. Classic example of work. I'm going to draw a pink box because I like boxes and I like pink. Here we go. Move that a little. Oops. Move that a little over here, and I'm gonna rotate that actually. And I'm rotating it just to represent that we don't have to be on the x-axis. We can be at some sort of angle. I'm going to draw an arrow. I'm going to draw that arrow in blue. That's going to represent my force here. And then I'm going to draw another arrow. That arrow will be in, let's go with green, a nice light green. There you go. And that will represent my displacement. So this box has moved along this line, this little line. And I'm going to draw this delta R, that's my displacement, and the force over here. So this is sort of like a classic work setup. Okay, so work is defined as F dot R. So I'm going to rewrite this equation. I'm going to write it as F, the magnitude of F, times cosine theta, and then times, where's my nice light green, times delta R. Okay, now what does this actually mean? Ooh, that is terrible, but it's okay. What does that actually mean? Well, if you remember from intro physics or maybe just trigonometry, the magnitude of F times cosine theta, well, that's just the horizontal component of force. So I can split this force up into two different components. I'm going to do that. I'm going to draw the arrow. I'm going to draw this horizontal component, and maybe it comes out to here, and the vertical component that comes up here. And I'm saying horizontal and vertical, but really I should be saying parallel and perpendicular. Parallel and perpendicular to what, you ask? Parallel and perpendicular to this one, this delta R. Okay, so I'll label those F parallel, F perpendicular, and this F, the magnitude of F times cosine theta, well, that's just the parallel component of the force. So what are we learning about work? We're saying that the work done is only concerning the component of force that is parallel to our delta R. So the last thing that I want to do in this video, and we've got 2 minutes left, is to look at this equation and figure out what is it that we're assuming about work, right? Or are we making any assumptions at all? So the first thing that I ask is, are we assuming that F is constant? So I'm going to rewrite it down here. Work is equal to F dot dr, or delta R. Get a little ahead of myself. There we go. Are we assuming that force is constant? Well, force is a vector, yes, but we can also describe it as a vector field. And if you've taken multivariable calculus, you know that we can describe this as a vector field in terms of x, y, and z. We can describe forces that have different values for every point in three-dimensional space, right? And we can still plug it into our equation, and we can still, if we can define it, we can get an answer for work. So we are not assuming that our force is constant, right? And the reason that I asked that is just because there were many problems in intro physics that had constant forces, but we're not we're not saying that here. The second thing that I want to ask is, are we assuming anything about delta R? Well, delta R is a vector, so the vector by its definition is a line, it's linear. So a big assumption that we're making about our displacement here is that it is linear. Alright. And in the next video, we're going to look at a case in which the displacement is not linear. The path that is taken is not linear, and we're going to see how that affects the equation for work. So more to come.